So hello, I'm Sunmyon Chon, and so thank you for giving me a chance to have a talk here. And so yeah, I'm Sunmyon from MPA, and today my talk title is Transition of IMF in the Early Universe. And so there was a very good review from Rafael and Alex, and I'd like to talk about how the subformation property transitions from first stars to the present-day universe. And today's talks are based on these three papers, which are already published, and the collaborators related to the today's talk are listed here. And okay, so one of the big goals of today's talk is to understand the origin of the tension between the recent JWST observation and the current simulation. And this left panel shows the UV luminosity function estimated from the recent JWST observation, and also luminosity function taken from the numerical simulation, which assumes standard galaxy formation model. And actually, so we can see that there is an order of magnitude difference in the abundance of the UV luminous galaxy. And one simple solution to reconcile this tension is that we consider top-heavy IMF or a higher star formation efficiency in the early universe. And if we have top-heavy IMF in the early universe, so it can boost the UV emissivity per fixed stellar mass that boosts the UV luminosity of the galaxy. And if we consider higher star formation efficiency, then stellar mass increases per fixed gas mass or halo mass that also increases the number density of the UV luminous galaxy. And so many models are proposed, for example, stochastic subformation model or just attenuation-free model. But today's talk, I'd like to focus on the possibility of the top-heavy IMF and higher subformation efficiency. And in fact, in recent our three papers, we have shown that top-heavy IMF can be realized in low metallicity environment, or even the metallicity become higher. So in the early universe, high CMB temperature can make the IMF top heavier. And also in this talk, I'd like to focus on how the star formation efficiency changes for the different metallicity environment. Okay, then firstly, I'd like to briefly overview the theoretical basis of the IMF transition. And left panel shows mass IMF or mass distribution of the first star, taken from the simulation by Hirano 2015. And actually, there's still no observation of this first star, but we can from the simulation theoretically we can infer that the typical mass of the POP3 stars or first stars are thought to be very massive as several hundred solar mass. But if we look at the local universe, the typical mass lies around 0.1 or 1 solar mass. That means the stars are dominated by low mass stars. And these two figures indicate that at some point in our universe, there should be some transition of the stellar mass or IMF transition should occur from top-heavy IMF to the sub-beta IMF. So the key question here is what drives this IMF transition? And important physics is the fragmentation physics, and it is also so much related to the cooling efficiency of the gas cloud. And these three panels show the cloud density distribution for three different cooling efficiency. And the leftmost panel shows the density field when the cooling is a very inefficient case, and we can see that cloud structure looks so smooth. But if we increase the cooling efficiency, we can see more and more fragmentation occur, and the mass of each fragment gets smaller and smaller. That might lead to the smaller stellar typical mass, and also might this higher cooling efficiency can cause the transition of the IMF. So the important physics is the cooling efficiency. So the next question is what determines the cooling efficiency? And one of the most important ingredients is the cloud metallicity. And here I show the temperature evolution of the collapsing cloud core for different metallicity cases. And from this figure, we can see that as the metallicity increases, the typical temperature decreases due to a higher cooling efficiency. And in this case, we may expect more fragmentation and smaller typical stellar mass. And so that means so higher metallicity environment can cause the transition of the IMF. But still we only focus on the physics of the fragmentation. But to fully understand the nature of the IMF, so we should also focus on the accretion physics. So accretion, because fragment also accretes mass, and also protoster inside fragments also accretes a mass. So this accretion is also important process to build up the IMF. So to understand how the IMF transition occurs, we need very high resolution simulation which can follow the fragmentation, and also we need long-term simulation which can follow whole accretion physics for around 1 million years. And to this end, here we have performed radiation hydrodynamic simulation using Galaxies code. And in this calculation, we resolve the gas density down to 2 times 10 to 15 per cubic centimeter, and also we resolved around AU scales around the protostars. And once this very high dense gas region appeared, we introduced so-called sink particle, which mimic the accreting protostars. And in this calculation, we also solve the non-equilibrium evolution of the thermal energy consistent with the low metallicity gas microphysics. And we also include a radiation feedback from the massive star that photoionize surrounding gas and photodissociate the surrounding H2 molecule. And in this calculation, we start from isolated turbulent monoinverted sphere with 6,000 solar mass. And we fix the initial condition and just change the metallicity from 10 to minus 4 to solar metallicity. And so purely focus on how the metallicity effects change the mass distribution or IMF. Okay, so let's go on to the result of our calculation. And so this is the movie for the initial collapse phase, and starting from very turbulent cloud core, so cloud collapses, and at the cloud center, so the very dense so-called protostellar cores are formed. And these panels show the density structure and the temperature structure at the formation epoch of the first protostar for 5 different metallicity cases. And we can see that the cloud morphology depends so much on the cloud metallicity. For example, when the metallicity is higher than 10 to minus 2 solar metallicity, so the filamental structure develops due to the initial turbulent structure. But so when the metallicity is below 10 to minus 3 solar metallicity, such a filamental structure decays, and 1 or 2 massive cores are formed at the cloud center. And the reason why filamental structure disappeared is due to the lower cooling efficiency. And it makes gas temperature higher and also pressure higher. And so this higher pressure gas easily erases the fine structure created by turbulent velocity. And in this calculation, we further extend our calculation to the point of 2 million years after the initial protostar formation. And the left panel shows the density evolution in the case of solar metallicity. And in this case, we can see that first the filamental structure develops, but it fragments into so many protostars. And at some point, feedback starts to work, and H2 region starts to expand, and the entire cloud gradually starts to be disrupted. But in the case of lowest metallicity case, for example, 10 to minus 4 solar metallicity case, so initially there appears a very compact cloud core and massive star formed inside, and at some point suddenly feedback works and entire cloud also suddenly disrupted. And this figure is our main result, so which shows the mass distribution or IMF at the end of our calculation for 5 different metallicity cases. And we can again see also the IMF so much depends on the cloud metallicity. And for example, in the case of the lowest metallicity, 10 to minus 4 solar metallicity case, we can see the log flat-like IMF, which is often observed in the first star formation. But as we increase the cloud metallicity, we can see number of low mass stars gradually increases. And if we look at the solar metallicity case, we can fully recover the salpeter or Kavli IMF. So the important message here is that the IMF does not suddenly change, but gradually transition from top heavy to the salpeter IMF. And actually, so we can see the slope of the mass distribution. So starts from -1, and so it gradually gets steeper and steeper, and finally it becomes a salpeter slope. And it also so increases the UV emissivity in the lower metallicity environment. And so left panel shows how the UV emissivity increases against the cloud metallicity. And we can see that when the metallicity is smaller than 10 to minus 2 solar metallicity case, UV emissivity increases almost by a factor of 4. And right panel shows the evolution of star formation efficiency found in our simulation and versus the UV emissivity for the 5 different metallicity case. And this white region is expected region where UV luminosity function can be consistent with JWST observation at redshift 15. And from this figure, we can see that only when the 10 to minus 2 to 10 to minus 3 case, so the value become consistent with this JWST observation. Above that metallicity, so because of the IMF transition, UV emissivity decreases. And below that metallicity, star formation efficiency decreases due to the lower cooling efficiency and higher temperature of the H2 region. And so in this case, so only this metallicity case is compatible with JWST observation, but still, so JWST observes more higher metallicity environment. But here we only consider the metallicity effect. So there is another very important effect, so CMB radiation. It can also make the IMF more top heavy. And so this is the last slide. And we also did how the CMB heating effect changes the IMF. And so this is so left panel shows okay, so evolution of the typical stellar mass as a function of redshift or so temperature of the CMB. And we can see that when the metallicity is 10 to minus 1 solar metallicity, so for example, so the typical stellar mass increases as the typical redshift increases. And so right panel shows the mass distribution of the relatively higher metallicity case, so at present day or so higher redshift universe, and we can see that even when the metallicity is 10 to minus 1 solar metallicity, due to the CMB radiation effect, so IMF can become top heavy, and it increases UV emissivity and almost by a factor of 2 or 3, and so this makes our results so consistent with almost consistent with the JWST observation. And actually, so this comes from relatively simple model, and so we recently combined our results with semi-analytical model, CAT simulation by Alessandro Tringa, and actually, still it is post-processing their result and just changing the UV emissivity, but okay, including our results, around redshift 15. Maybe the number density of the luminous galaxy increases, and still it is consistent with maybe number density of a spectroscopically confirmed one, but still a bit smaller than photometry one. But maybe the next step, we need to include combine our results with hydrodynamic simulation or semi-analytical model. Okay, thank you for listening.
Thank you, Sunmyon.
Just a naive question.
What
does top heavy mean?
Top heavy. Okay, top heavy means, so the number of massive stars is higher than the usual local universe that observed in local universe.
A larger fraction of stars with high masses.
Yeah.
Many stars with high masses.
Yes.
Over there.
Thank you very much. Have you looked at how the ambient density of the stars forming will affect IMF as how you enrichment density? And also, when you have high density, how's the radiative feedback from stars?
So you mean initial gas density or density around stars? Around the stars. Actually, so in this calculation, we only include radiation feedback, and so we do not include stellar wind or supernova feedback, so forth. And so maybe, yeah. Actually, so one of the problem is because we are probing also to the lower metallicity environment, it's still mass loss rate is still uncertain. But maybe so you are considering stellar wind or so.
Yeah, so I think there's a possibility we have a high density, and there's a balance between the stellar wind and the accretion of the stars.
I see.
Which will make massive stars still weak.
Yeah, I see. So feedback from the stellar wind is maybe next step. Maybe we should consider. Thank you.
Andrea?
Andrea, it's me. So thank you for the talk. I agree that actually making the IMF top heavy, it's an intriguing possibility to explain many things that we see. On the other hand, I think we have to be also careful in drawing conclusion from the fact that the stars produce more feedback, more metals, more dust, perhaps also more black holes, and so you have to because having a larger L over M is not enough if you don't include also the fact that perhaps the efficiency will be depressed because you have a lot of feedback from more feedback from the stars, and therefore you increase the L over M per star, but then the number of stars that you form is decreased. So it's a balance.
Yeah. Actually, next step would be including maybe increase the supernova feedback rate and considering everything makes consistently, and for example rebuilding the semi-analytical model or hydrodynamic simulation, or actually there's so many ways to.
Ali?
It's just a comment on that. I think Andrea's right that the sort of radiative feedback and the stellar wind feedback will increase with the top-heavy IMF, but as sort of Alex just talked about, we don't know the upper mass limit of the stars that explode, and so, I don't know, let's assume it's somewhere between 25 and 40. If you make the IMF slope so top-heavy, you actually get less feedback. True. But it might come out as wins, right? So I think I've heard a number of times that a top-heavy IMF means more feedback, which lowers the efficiency, and I think the jury is still out on what actually happens here.
Just a comment, as I showed in my talk, that's again not necessarily the case that a top-heavy IMF does not necessarily mean a significant impact on the star formation efficiency if you can form your stars in very dense compact associations. I also agree the jury is still out on the interplay is not as direct as you might imagine.
Yeah, so can I comment on this? And actually, in our simulation, we start from relatively less dense cloud. Actually, but still we don't know what is the typical initial condition for lower metallicity case. And if we can start from more and more massive and dense gas cloud, maybe actually we can suppress the star formation. So feedback efficiency, and and maybe it might also change the IMF or so. And actually, starting from another initial condition, and so knowing what is the true initial condition would be also next step.
Okay, thank you again. And can Chon please come forward for the first lightning talk?